Okay, HVAC class, let's get rolling here. I hope to get through this document by the end of Thursday's class. We actually had talked through this. 19 was the figure that's missing that I did email you guys. And it's this same figure that's 20. It just, this is with the pump off, 19 is with the pump running. But so this is showing with the pump off, we simply don't take any of the crossover flow, and it simply goes from the primary supply over to the return, pumps off, so the secondary is dead with no flow. We're showing there. There you go. See if I can get this thing to roll. There we go. Okay, let's see. This is an example where I've got my crossover flow is 10 and my secondary flow is 20. So when the pump runs, I simply pull all of this 10 up into the secondary. And also, since I'm pumping 20, I've got to transfer of this 10 GPM of this return water backward through the common pipe. They mix right here at the T or just downstream, and that mixture gets pumped through the coil. So 10 GPM in the crossover. The common pipe's got 10 going the other direction, and then my 10 return goes back to the return. This stuff pretty simple after you kind of get the general concepts. And this is the same system, just with the pump off, and so then the 10 just bypasses from the primary supply through the crossover bridge over to the primary return. I think we probably did those last time, but anyway. So let's look at, this is new. This is what we call an injection pump. And so the advantage here is that we can run our secondary pump all of the time. So it's noted continuous pumping. And what that gives us is freeze protection on the coil. And so if the air going across that coil has access to outside air, then we have freeze potential. And one way we can avoid that is by continuously pumping the secondary. So this is a good arrangement for that. So let's see, where this is one where secondary and crossover is the same. So let's see, in this one, the injection pump is on. So what this injection pump is an additional very small pump that's added. And so we've got the secondary up here, and we've got the crossover down here, and then we simply put these injection risers, they call them, where I can get this, if I run the injection pump, then whatever that flow is gets pulled out of the crossover and injected into the secondary, which is continuously pumped. If this doesn't run, then this primary flow just bypasses and stays down here in the crossover bridge and goes back to the return. So we're showing all of this as 20 GPM. So with the injection pump on, I've got my 20 GPM coming up into my crossover bridge. All of that then goes up this injection riser to the secondary. And so since it's flowing 20, all that 20 then gets pumped by the secondary pump through the coil. And then it comes back down to this second injection riser. It gets pulled down by the injection pump, put back into the crossover bridge, and goes to the return. So pretty slick operation. So here's the similar system, but now, this is with the pump off. Okay, so it's exactly similar. It's exactly the same. And so with the injection pump off, we have no flow through these risers. And so all of this 20 GPM just bypasses, goes back to the primary return, and we're simply pumping water around in a circle in the secondary. Okay. And now this is one where I've got 20 GPM in the secondary and 10 crossover. So this would probably be a heating situation where I've got some pretty hot water in my primary, and then I'm going to temper it when I bring it into the secondary by mixing at this T up here. So the crossover is 10 GPM, the pipe size for that. The injection riser is also 10 GPM, coming back down 10 GPM, the pump size for 10 GPM, all of this. And then I've got 20 GPM, so my secondary is size for 20. And so when the injection pump is on, I've got my 10 GPM or primary coming in. I've got my 10 GPM of return water from the secondary that's coming through the common pipe backwards to the mixing point, or towards the pump, I should say. It mixes here. And so, you know, the temperature of that mixed water, if I'm 10 GPM and 10 GPM, then it's going to be just the arithmetic mean, pretty close. So if this one, let's say this was 200 in the primary, and let's say this is size for 140, leaving coil temperature, then that's what, a 60-degree delta T, so half of that's 30. So I'd have about 170 here that's being pumped into the coil. So then the coil would see what, 170 minus 140, or a 30-degree delta T. That's kind of the way that works. And let's see, this is the same except the pump's off. Now we're just circulating 20 through the secondary, and we've got our 10 that's just going across the crossover bridge. Injection pump is off, so I got no flow up through these risers. Pretty simple. Okay, we can do the same sort of thing with a three-way modulating, or it could be two-position or modulating valve. So let's see, this one we're showing 100 GPM every place, 100 GPM in the crossover, 100 GPM in the secondary. Again, we've got the secondary pump running all the time. So this is where this valve is set to pull 100 GPM out of the secondary and put it down the riser. So that's going to cause 100 GPM to flow up into the secondary. You can think of that pump sucking it up there if you want to. And so then it just gets pumped around through the system, comes back down through the valve, and we've got no flow in the bypass down here. Okay. Then we can go to same situation. We can take the valve to a 50% position. So I've still got 100 GPM in my crossover. I'm allowing 50 of it to bleed through the valve and go straight to the return. The other 50 is being pulled up into the secondary. So this is 100. So if I got 50 coming up here, I got to have 50 in the common pipe return. So again, I get a 50-50 mix. And then so I moderate the temperature that goes to the coil, comes back around. So 50 here, 50 back down. This 50 return mixes with the 50 that came through the bypass, and I got 100 GPM going to the return. Let's see, and this is, let's see, what are we doing here? Oh, okay. So now I've got the crossover bridge size for 50 GPM. So see, these like this are most likely a cooling situation where you want the same temperature. You know, if I've got 42-degree chill water, most of the time I'm going to want 42-degree chill water through my coil. Okay, so that's kind of what that's all about. But in a heating situation, then I may well be doing something like this, where because I can make this water super hot, then I can downsize the pipe and downsize the flow, which saves me money on building the system. And then I can take that super hot water and just mix it here. So I don't, because if you put too hot of water in this coil, it makes it hard to control. Then you're probably going to overheat people. Or you can make air so hot that you could burn somebody if they brushed up against a register, and you wouldn't want to do either one of those. So, okay, so we got crossover bridge size for 50, secondary circulating 100. And so if this three-way valve closes off the bypass, then all of that 50 is going to go up into the secondary. It'll mix with 50 back through the common pipe. And so I get 100 here. I reduce the temperature some, and then I pump the coil with that, come back down, and my 50 of my 100 comes down through the three-way valve and gets returned to the primary. Okay, this could be an intermediate situation. If this is set up to be a modulating three-way valve, then it can go any place from full flow to full bypass. So this is the 50-50 situation. So now of my 50 to the crossover, this valve is kind of in a 50-50 situation. So it's allowing 25 GPM through it, and the other 25 is going up into the secondary. So then I've got 75 GPM up here mixing. And so, you know, I'm boosting that temperature a little bit. So see, by controlling a modulating valve down here, I can set this secondary temperature to be whatever I want it to be. Any place in between. On the low side, it could be just return. And on the high side, I guess it could be a 50-50 mix, because I've got just 50 here and 100 here. So, and it's very easy to control that sort of thing. We'll talk a lot more about it as we go through this stuff, these figures today. Okay. We can also use two-way valves. Okay. So if we're going to do a two-way valve, we'll set it up like this. And so this is, let's see, I'm showing a crossover bridge flow of 20. And this valve is wide open. So I've got my 20 going up into the secondary. So now I've got 80 GPM mixing. So I'm boosting the temperature a little bit, and I pump the coil with that. I come back down, my 20 goes back down through the control valve here, and back to the primary return. I have to have a little balancing valve here. I have to induce a little pressure drop between these two pipes, because this is a common pipe. And the general theory on a common pipe is you don't want any pressure difference. You don't have any pressure difference, you don't get any flow. So this then has to be balanced right. So when this valve goes wide open to 20, I get 80 through here and 20 up through there. So in this case, you have to, with a two-way valve, you have to induce a little pressure drop. And we have some flow control valves over here. We'll talk about those here in a minute, what those are there for. And they have a very small pressure loss. And then, of course, this valve has some pressure loss across it as well. Okay. So this is the same situation where we're in like a 50-50 position on the two-way valve. So of my 20, it's coming up to my crossover. This valve is open to the point that I get bypassing, which means I get 10 up through here. So now I've got 90 GPM through the common pipe mixing with the 10, you know, a little boost in temperature, and then I pump the coil, come back around. So same situation, we've just modulated the valve to allow 10 GPM to bypass the secondary. Okay, so this is the same. Now we've shut the valve completely, so we don't let any flow down here, so we don't take any flow up into the secondary, and the whole, you can think about the 20 simply bypasses and goes from the primary supply to the primary return. Okay, so let's look at some of these notes. And this should say crossover bridge. There's a old Bell and Gossett. They didn't edit this thing too close. I think the basic information is pretty darn strong, but their editing could be better. Crossover bridge to secondary circuit flow relationships. Each secondary circuit is served by a crossover bridge, which supplies necessary primary water. So, you know, we could have, you know, 10, 20, 30 of these. I mean, you can have a whole bunch of them in a system. Okay, so each one is going to a particular coil that's conditioning a particular space. Required crossover flows are established by secondary circuit heating or cooling needs. Well, how much do you need? It depends on what's the load, what's the capacity of this coil. Is it 10,000 BTUs an hour? Is it 100,000 BTUs an hour? Is it 1,000,000 BTUs an hour? Okay. And so once you know the capacity of the coil and the design condition, you set your coil entering and coil leaving, you get your delta T, then, you know, Q is 500 GPM delta T. It's a simple calculation to solve for GPM. And we'll be doing a bunch of that as we go forward. Okay. There are two conditions that must be evaluated, and we've been over that umpteen times. Secondary circuit temperature equal to primary temperature. So that means that, you know, we've got the same, basically the same flow rate up through here. I mean, you know, if the flow rate between the the primary water entering the secondary is different than the secondary, then we're going to have some mixing going on, and that's going to moderate that temperature. But if all of these flows are the same, then I'm going to get the same temperature. And of course, the second case is secondary circuit design temperature different from primary, probably lower, and it's probably a heating situation where the primary is hot water. And so more notes, but we need to pay attention to these notes. When you go back and study, you need to, there's not a whole lot of verbiage. The good news is you can go through this. It's 50 something pages, but you can actually go through this thing in, I don't know, 2 or 3 hours, because there's not all that much. And once you understand the diagrams, then you just, you know, move on. Most chill water systems are designed so that the secondary supply temperature equals primary supply temperature. We got 42-degree water coming, you know, in the primary. We want 42-degree water in the secondary. Pretty simple. This requirement provides a very simple design rule. Primary crossover bridge flow rate should equal or slightly exceed, and you may want to just slightly exceed it on the design to make sure that you have enough primary water available to go into the secondary. Because see, if you starve it, if you said you were going to have 100 GPM and you had 90 GPM, then and you're circulating 100 in the secondary, then you would be recirculating 10 and mixing, and then that 42-degree water would probably turn out to be 45 or 46, and maybe you wouldn't have enough capacity to air condition your space at the design condition when it's really hot outside. So that's just a little safety factor you can put in there. Many chill water systems, however, and most hot water can be designed so that the secondary circuit design water temperature is different from the primary water temperature. I would disagree on the cooling side. I don't personally think that's a very good idea. Now, depending on how cold your water is, I guess, you know, if you're running 38-degree water, okay, I'll buy it. But most chiller plants don't do that. A possibility for greatly decreased crossover bridge primary circuit flows is established, and that's by having really, really hot water to convey the heat in the primary. Following example is stated for pump on-off control. Design principles are general, however, and can be applied to any of the other possible control methods: injection pump, 3-way valve, or 2-way valve. So here we got a little example. So let's take a look at this. I guess I should read it. There we go. Example number 1. Secondary circuit is designed for 140 mean water temperature at a 20-degree drop. Mean water. So that means if it's 20-degree drop, so that means our supply is 150 and our return is 130. Because, you know, if 140 is in the middle and I got a 20-degree drop, I got to add 10 and subtract 10 to get my supply and return out of the coil. Total secondary load is 200 MBH, that's 200,000 BTUs an hour. Establish required crossover bridge flow rates for a series of possible supply water temperatures ranging from 150 to 300 degrees. Excuse me, my phone was attacking me. The circuit is diagrammed below for an initial 210 supply water temperature. So we're going to work all the numbers at 210, and then we'll show a table for the other supply water temperatures. Well, okay, so I said we got 150 in, 130 out. That's pretty simple, okay? So if you got a 20-degree delta T, if you got your calculator handy and want to punch some numbers just to see how this, I mean, this stuff's pretty simple. So if you just look at the coil, we've got 200,000 BTUs per hour. So if Q is 500 GPM delta T, which we use for this sort of stuff. Now, that's not 100% correct because that 500 number assumes like 60, 70 degree density of water. And as you go up in temperature, that number changes a little bit. But within the amount of accuracy and all that stuff for a typical building, it works out fine. But, you know, I mean, if you were doing this in Excel or something, you could go ahead and look up the actual density and, you know, it's m.cp delta T. And of course, you know, your density changes, specific heat changes a little bit, but it's probably not going to change your overall design. Okay, so anyway, I'm going to use Q as 500 GPM delta T. And so Q is 200,000 divided by 500. And then my delta T is 20 divided by 20. And the result is 20 GPM. So that establishes I got to have 20 GPM circulating in the secondary. Okay, and you see he's got it noted at 20 GPM. But now we got to go down and figure out what's our crossover. Well, if you think about it, if I look at my secondary, I'm sorry, if I look at my crossover, I've got 210 degree water coming up, and that's what has to convey the heat, and I got 130 return. So whatever that flow rate is, it's going from 210 to 130. Okay, well, so I still have to convey 200,000 BTUs an hour. So if I take 200,000 divided by 500 divided by open, because I can't subtract in my head, 210 minus 130, that's 80. So that's 5. So right there, to convey 200,000 BTUs into that secondary with 210 degree water with 130 return, I got to have 5 GPM. So what's going to happen is I'm going to take, when this pump runs, I'm going to take 5 GPM. 5 GPM is going to be sized here. It's all going to come up in here, and I'm going to take what is it, 20? I'm going to take 15 GPM back here, and I'm going to mix, and that's going to give me my 150 that then is going to go through my coil. Now we'll see as they do calculations here, but I just wanted to talk through. So I mean, the good thing about this is they really do go through it step at a time to make sure that you understand. Step 1, determine crossover bridge temperature drop. Point A, crossover bridge return water temperature will equal secondary return water temperature, in this case 130, because you know I'm going to, when this thing, I got 130 here coming down here, and when this pump runs, this flow rate is going to come down and go right down here, and there's not, because when the pump runs, the flow is going the other direction in the common pipe. So I don't have a choice. If I got 130 here, I'm going to have 130 there when the pump runs. Oops. Oh gosh, what did I do? Okay. Okay, so assuming primary crossover bridge supply temperature is 210, crossover bridge temperature drop will be 80. Just subtract them. And then that's how I calculated the 5 GPM. I have to deliver 200,000 BTUs an hour from my primary water into my secondary. So 200,000 divided by 80 is the temperature difference divided by the constant 500 gives me 5 GPM. And Bell and Gossett makes what they call this system sizer. It's a little circular, like a slide rule, but it's a circle. And you can do all these little calculations simply on the system sizer. You could probably send them an email and they probably send you one for nothing. You know, I'm sure they would. Tell you you're a student at Tennessee Tech and you want a free system sizer. I bet you they'd send you one. Or you could contact Bell and Gossett in Nashville. You just call them up and say, hey, I'm graduating at Tennessee Tech. I want one of them system sizer things. So they'd send you one. Okay, determine the common pipe flow rate. Well, I mean, it's pretty clear. If I've got 20 GPM up here and I've got 5 going up there, I got to have 15 coming back here. You know, it's kind of what continuity says. So that's pretty simple. And then you can, now let me see, are we done or did I skip over? No, I guess that's it. Okay. In order to illustrate the general nature of crossover flow determination, the modulating three-way valve application flow diagram for full load conditions is stated. So, you know, we can do the same thing with a three-way valve, and now we can run this pump all of the time, right? And then the three-way valve will control when that 5 GPM goes up here, if a portion of it goes, or if it all bypasses and comes back down here. So under this situation, if I don't need any heat up here, then that 5 GPM would just come across and I wouldn't be taking any energy out of it for the secondary. And let's see, the 150 supply temperature as mixed temperature results from the 5 GPM of 210 plus 15 GPM of 130, and you can do a little heat balance, right? So if you do the 15 GPM times 130 degrees plus 5 GPM times 210 is equal to 20 GPM times question mark, and then you can solve for 20 if you want to, or he just punches it. When you do the math, you see that balances. Okay, so, or you can do a little equation like that and calculate the mixed temperature if you want to, whatever you need to do. Required primary crossover flow rates are illustrated in table 1 for a variety of primary supply temperatures. So here's where we really see the benefit of this. So it takes a minute to think about this table, but once you think your way through it, it's pretty simple. So over there on the left, we've got the primary crossover bridge temperature. So the lowest it could be is 150 because that's what we want to put through the coil. That's what we size the coil for. And the highest he's run is 300, okay? Well, so our primary crossover bridge return temperature, that's the temperature coming out of the coil. It's going to be 130, no matter what the primary supply water temperature is. So then now we can get the primary crossover bridge temperature drop. Well, it's just this number minus this number. So you see, if the primary temperature was 150, then we'd only have a 20-degree drop. And I would need all 20 GPM from my primary. So if I go back up, say if this was circulating at 150, then I'd have to have 20 GPM. I'd pull it up here, and then I'd pull it up in here when I need my design capacity, and it would circulate around and 20 GPM come back down and into the return, okay? But as I go up in temperature, if I go to 170, then my primary crossover bridge drop is 40. Oh, and I only need 10 GPM, which means I have, you know, downsized my primary system a little bit. Secondary flow rate's going to be 20 for all of them. And this is the common pipe flow rate in order to mix, in order to provide the 150. So then see, I'd have 170 mixing with 130. I'd have 10, that's a 50-50 mix. So I'd have 10 GPM of primary water mixing with 10 GPM of common pipe water to provide my 150 that then goes to my coil. And likewise, so at 190, then my delta T on the crossover is 60, and my flow rate's down to 6.6 GPM, and my mix common pipe flow is 13.4. At 200, my delta T is now 70. I'm down to 5.7 GPM. Again, secondary is 20 on all of them, and I'm pulling 14.3 GPM of 130-degree water back to mix with the 200-degree water to get my 150 to go into the coil. And so I think I've said that enough, but so you look down and look what happens to the required crossover flow for the same heat conveyance, 200,000 BTUs an hour. At 300 degrees, I only have to circulate 2.4 GPM, and I'm mixing with 17.6 in order to get my 150. Well, if that primary system's a big system, if I size it for 250 or 300 degree water, I get smaller pumps, smaller pipe, less cost. And so, and I don't affect the operation of the secondary because I'm going to temper the water in the secondary with the mixing of that return water. So this is what's so powerful about this primary secondary, especially for heating systems. Okay. This example illustrates one of the outstanding advantages to primary secondary pumping, that the primary circuit can be designed for very high temperature drops so that both primary pumping and pipe costs can be reduced. It should be emphasized that the primary circuit serves only a heat conveyance function, and that its temperature drop or rise can be entirely different from the secondary. So that goes with that table above. Okay. Let's look at, we got lots of different applications here. So start-stop pump control of secondary circuit. This control application is a simple adaptation of a control method proven in several million residential systems. So anyway, just a comment. I don't really care about that or not. But anyway, so you got a thermostat, you got hot water available, and when it's cold, you know, you get some kind of delta T on the thermostat. Thermostat says it's cold in here, Mr. Pump, you need to run. Mr. Pump runs, it pulls hot water up into here. It may do some mixing. If this is high temperature, probably does. We temper it, goes through the coil, back down into the crossover bridge. So let's see, the only real difference between we don't really care about that. I'm going to skip over that note. It's necessary. Okay, there is a comment, this secondary comment, we get into this on this next paragraph. It's necessary that water flow from primary to secondary be absolutely prevented during the pump off thermostat satisfied condition. Well, sure, when when your space is satisfied, you don't want to be putting more heat into it, you'll overheat it. And so when that pump goes off, we got to make sure that we don't have any gravity circulation or any natural convection flow up into this pipe that could warm water, that could get into the coil, that could then, if you may be blowing air across that coil all the time, or that could be a radiator on a baseboard. And if you put warm water in that coil, you're going to get heat out of it, and you might lose controllability. So flow control valves prevent hot water flow caused by gravity heads or by the slight pressure drop established across common piping when the secondary pump is off. Okay, so And we got more detailed diagrams below. But we try to make this common pipe as short as possible so we don't have any pressure drop across it, but you're going to have some pressure drop. I mean, that's just the world of friction. You can't really help that. So there is some slight pressure drop, which could, with flow through here with this pump off, try to force a little bit of water up through this secondary. Also, if this is hot water, say this is 250-degree water and this is 130-degree water, you're going to have the possibility for natural convection currents to set up inside the pipe that can pull some of that hot water up into this secondary, especially if this is, a vertical connection with this pipe coming up straight, because that warm water is going to want to rise into that cold pipe. So, into here, but don't worry, don't fret, because Bell and Gossett has made a valve to fix this, and they'll be happy to sell them to you, as many as you want. Okay, so flow control valves are weighted check valves and are used to block flow as induced by slight common piping pressure drop or by gravity heads. They're generally needed whenever pumps are used for control. Okay, so that's what these little kind of check valve, this is the symbol for a check valve. So these are these little flow control valves, and they put them in where they think they're needed. And there's a little, not a very good picture. I'm sure we could go on the internet and find a better one, but nonetheless. So, and for the Bell and Gossett, when the stem's down, it's working, and when the stem's up, it's wide open. So you don't want to leave the stem up. Flow control valve is statically weighted to approximately 0.6 of a foot of water head. So it is an automatic check and anti-gravity flow operation when the stem is turned down. The valve is open and will not perform its anti-gravity flow function when the stem is turned up. So we want to be sure we know that. Okay, so that's what these little Z's with the dots are, these little check valves are in these diagrams. They're these flow control valves to eliminate flow when we really don't want it. Need for 2 flow control valves, start, stop, pump control. Okay. 2 flow control valves are generally illustrated for application with start, stop, pump control of secondary circuits. This is because gravity flow can occur within a single pipe, as is shown in the figure. So we got a blow up of the connection. And so see, we've got a vertical connection. And so see, that hot water is going to want to rise, and this cold water is going to want to flow down into this hot pipe and mix. And that's going to put this hot up into the secondary, and it's going to happen on both of these pipes. So if you get enough of that going on, you could just increase the overall temperature in that secondary, especially if it's a fairly small volume of water. And then you're putting heat into the space when you don't want heat into the space, and you lose control. Okay, so that's what that's all about. Okay, a single flow control valve can be used when the secondary circuit return riser is underslung. So if we undersling the secondary, if we have room to do that, then we can avoid buying one of those 2 valves. So see, they show it over here because we're showing a direct vertical connection up, but this one is, it drops down below, and I think we need at least 1 foot of drop underneath the crossover for this to be effective. Underslung return riser, thermal drop leg, 1 foot prevents gravity flow. So you could undersling the secondary return pipe into the crossover, and that would eliminate the potential for gravity flow. You guys are learning all kinds of good tricks here, I'm telling you. But I mean, this is kind of getting down into the nitty-gritty. I mean, all of this stuff is not complicated, but to design a successful system that's going to function well, this is stuff you need to know. So anyway, single pump control applications. Start and stop operation of the secondary pump has been used for controlling a variety of applications. Some of these, we're just going to look at some different pictures. Okay, so this would be baseboard heaters. Again, if you've got a big atrium or a lobby, this happens in really nice fancy hotels and stuff like that that have a lot of glass around. They can disguise these things pretty well so that you really can't see them. The architects that I've worked with don't seem to mind, and so you can put this in. And so, you know, it could be a hotel, people coming in and out a lot, or, you know, a big office building or something like that. And you got to keep that big area with all the glass warm in the winter time. Lots of air blowing through the doors because they're opening and shut a lot. And so you can put in a situation like this where you put all those baseboard heaters in, and you could be one, you could have several circuits, whatever. And when you get below set point, the pump runs and you pump some good warm water through those coils, and by natural convection, that heat rises into the space. So that would distribute it pretty nicely. So that's a possibility. And of course, we see on this one, we see double flow control or double check valves on it. Existing supply or return main. So this comes up when maybe you have to add a coil and you don't have a supply and a return pipe close at hand. So this is where you pull, and this would probably be a pretty substantial flow. You pull a little bit off and you run it through a coil, maybe you add a guard shack or something. You got a hot water line running by. You got a 6-inch line, and you need 20 GPM or something. It's not going to make much difference. So you just pull a little bit of that water, pump it through this, and dump it back in the same pipe. So you've cooled it down, but if it's a big flow in the supply or return main, it's not going to make much difference if you just take a little bit of heat out of it. So you can do this. And so on this one, say we're coming in from the bottom, and so we only show a check valve on one side. There we go. This could be a domestic hot water, for showers and stuff. You could have an apartment building, and you have to, generate the domestic hot water. And you don't want to put in more combustion. Say I've already got, a steam system, and I'm making hot water, and I got 250-degree water flowing all over the place. Why would I put in more burners and more natural gas piping and all that? All I got to do is get me a big tank, put a coil in it, and then pull some of this hot water. If there's 250-degree water, I can pull it in here and run it through that coil anytime that temperature, say I'm trying to maintain, 160. By the time I distribute it out, it's 150, and that's pretty good shower temperature. Maybe you do 170, whatever your design spec is. And so you just have a temperature sensor that clicks this pump on and off, and you got a little delta T. Maybe you run it from 170 to 175. And of course, as they pull water out of here, you're going to have makeup water go in. And so you would need to make sure that stays mixed pretty well in the tank. Or you might make up the water on the bottom and pull the supply off the top where it's hot and put the temperature sensor in the bottom where the cold water is. There you go. That would work. Now, this arrangement, and say this is our standard arrangement, we're pumping out of the crossover into the secondary. Okay. And he notes here supply water temperature less than 250. So this arrangement, which is not what we normally recommend, is if your supply water temperature is more than 250, look where he's put the pump. He's put the pumping into the crossover bridge, which is not where we typically want to do it, but it's because this water is so hot that you see after that hot water flows through this coil, it's not so hot anymore. And so it doesn't tend to overheat the pump. So, and he makes a comment down here that, well, let's see, figure 44 describes generation of domestic water or steam. You could actually, if this is hot enough, you could be generating steam in here. from medium temperature water distribution system 250 to 320. In this case, the secondary pump is placed in the secondary return in order to reduce temperature effect on the pump. This differs from conventional application, pump and secondary supply, but is almost always permissible for this application because of the generally low head booster pump requirement. So they're saying this is such a small pump and this, that, and the other that it doesn't generate that much head, that it's better to do this than to put it in the more conventional location. That could be a subject for discussion at the design firm. Where do we want to put this? Make sure that the pump is spec'd appropriately. Okay, so here's another example. So this is face and bypass damper control to eliminate heat wipe and permit deep temperature drop design of primary. Secondary pump off by end switch. Okay, so this is air that, this is mixed air. So you got return air, probably some outside air mixed in here. And then when you get, this is the coil setup. And so what I have here is, this is obviously my heating coil. So I can take my, hot water and run it through this. I'll probably temper it some. If I got 250 degrees, I don't want to put 250 through this coil. So maybe I'm running 170, 160, 150, whatever, through this coil. And these are called face and bypass dampers. So you can, the face would be, this air would go across the face of the coil. This would be bypass air. And then they mix over here to give the temperature that the space is requiring. Okay, face and bypass. But in the HVAC world, dampers leak. Okay. And so what they're showing here is that these dampers have closed, but we're going to put an end switch down here to cut off this pump because we don't have any confidence that I can stop all of the air from flowing across this coil. And if I put a little bit of air across this hot coil, I'm going to get some pretty warm air here, which is going to mix, and then I'm going to lose potentially control of my space because I'm going to dump heat into it when I don't want heat. It doesn't need heat. So a way to avoid this is to put this end switch in that kills the pump. And then if a little bit of air leaks across a dead coil, who cares? Now, you have to worry about freeze protection. So, it could be you're going to have some sort of a preheat coil back up here to make sure that I can't freeze this coil with a little bit of cold air leaking across it. So there's always something else to think about. But this is what we mean by face and bypass dampers. Here's one. Industrial process control, remote from the equipment room. So we've got a fluid out in the plant that we need to heat. So what is this? A shell and tube heat exchanger. And so I've got my hot primary water over here. So I've got a crossover, I can pull some up. I've got a temperature sensor on this fluid leaving the heat exchanger. I could have this thing, pretty close, maybe a couple degrees, and so it's gonna run this pump in order to maintain the temperature here. Otherwise, this water will just bypass and go back into the return. Temperature sensor control elements illustrated should be immersion bulb type with close differential, 1 to 1.5 degrees is what for good tight control of this fluid temperature leaving the heat exchanger. Okay, constant secondary pump operation, terminal unit control only. Secondary zone pumping is often used in large systems employing high head distribution pumps in order to eliminate shut-off head control valve problems. Okay, so these may be high differential head pumps because this could be a good size loop and it's got to pump a long ways and we got to have a lot of pressure to get circulation. Also because we've downsized the pipe because we're trying to save on first cost, so maybe we've run up the pump head a little bit. Well, with the crossover bridge, this big pressure drop from here to here, we isolate from the secondary. Because if these control valves saw that differential pressure, they would have to be God knows how strong to be able to close off against that high pressure. But because, say, the only delta P, these that we see across here are between the common pipe and anything that's generated up here by this. And so this is a small, relatively small low head pump. So that gives us controllability on the control valves up here in the secondary. Let's see. Since the secondary zone pumping is in continuous operation, okay, the flow control valves, the anti-gravity valves are not shown here because this thing is going to run all of the time. Okay. And of course, now the way this is drawn, this is interesting. If all of these valves were to shut, we would deadhead this pump, right? Because there is no bypass. We don't have a bypass or anything to give us a flow path around this if all of these valves shut. So you would have to make sure that this pump was small enough or small enough head that it could. Now, of course, you've got 2, 4, so you got 7. I mean, what are the chances all of them are going to close? I don't know, but it could happen. And, you know, Murphy is always lurking out there. Whatever can go wrong will go wrong. And it'll probably be on your first design job and it'll bite you in the tail. And somebody will yell at you because, oh, yeah, you deadheaded the pump and it burned up. Oh, dadgummit, I knew I forgot that. You know, whatever. So you would have to consider that in this case. Okay, injection pump control methods, secondary zone. Okay, this is pretty good. I like this. Okay, the injection pump has been widely used for reset control, both of boiler equipment in boiler room and secondary zones. Typical applications are shown. So now what we're showing here is we have a controller that has 2 bulbs, 2 sensors. One goes in the outside air and one goes, it could be a space thermostat. Probably if it's a reset, it's going to be a water supply. So like when it's really cold outside, okay, I can run the injection pump more. I can put more heat up here and I can have hotter supply water to my coils. I can have that schedule. So maybe when it's below 20 degrees, I want 170, 160, whatever your design point is when it's cold outside. But then when it's, you know, 35, 40, 45, I need a little bit of heat, but then you reset that down to maybe 150 or 140, something like that. And it gives your control valves for your coils better controllability because it doesn't have it's not trying to control a really hot, you know, if you got 180 degree water and you have a very small load, you pop a little bit of that in there and already you've overheated. If I have 140 degree water, then I can, you know, allow more flow, I get better controllability out of it. So anytime we see these dual sensors going into a pump control, we're probably going to be doing some sort of reset on it. Okay. Injection pump to space control or air handler. You know, your space thermostat could control that injection pump, or it could be a discharge air temperature on your air handler. It could be a lot of things. The heat injection pump operates on-off and injects shots of hot water into the continuously pumped secondary circuit on controlled demand. So we're going to run that pump. We're going to put a shot of hot water in there, pump that around. If we need some more, we'll put another shot, that sort of thing. Space temperature is controlled by a conventional electric thermostat operating the pump on-off through a relay. Reset temperature is obtained by an electric reset double bulb controller. Control is inexpensive, easily understood, and can be serviced by local personnel. Simple is good. Injection riser and injection pump sizing. The injection riser is sized to the full load primary crossover flow requirement, and in most cases is equal in size to the crossover pipe size. The injection pump is always sized to the full load primary crossover flow requirement. And we've got some illustrations here. So let's take a look. Okay, so let me see. So this one, we've got 40 GPM every place. We've got 40 GPM in the crossover. So we've got 40 GPM up here in the secondary. And so when this pump runs, we're going to pull all 40 GPM out of the secondary. We're going to put it here into the return side of the crossover, which will pull all 40 GPM up into the secondary. And so this is probably going to be a chilled water type application. So my primary temperature and my crossover temperature is going to be the same as my secondary temperature. And everything is sized 40 GPM, they're saying that's 2-inch pipe. So I've got 2-inch pipe, 2-inch valves, 2-inch flow controls. I got 2-inch everything in here, 2-inch common pipe. Okay, so that's the equal. And then in the second diagram here, now this is probably hot water because I've got my crossover flow is at 10 GPM and I got 40 in the secondary. I'd say I've got some pretty hot water looking at that ratio. This is probably a 220 to 250 degree system, okay? And so, again, and also notice that, you know, I've got balance valves in here, I've got flow control valves and all that sort of thing, because this pump, this injection pump has to have a little bit of head to pump against. You know, it just, you know, I mean, you won't have any, you won't be able to control the flow. So what you do is you put this stuff in, you put this balancing valve over here, they turn this pump on, they measure that flow, you know, they flow this. So they get all this stuff running and then they measure this flow up through here and they set that balance valve so that when this injection pump runs, I get my 10 GPM up from my crossover into my secondary. So that's all part of the balancing on the deal. And so, yeah, this is going to have some pressure drop, obviously, between these 2 points. That's what that balance valve is there for. But anyway, so I got 1 1/4 inch pipe, all of this that is expected to see a maximum of 10 GPM. But up here, since I got 40 in my secondary, I got to have 2-inch pipe. So that's, I think, pretty common sense. Let's see. Need for injection line flow control valve. Slight pressure drop caused by continuous flow through the common piping located in both the crossover and secondary circuits will cause a flow from primary into secondary with consequent lack of low load controllability. Flow control valves will prevent injection line flow except under controlled demand. So that's what these guys make sure that we're not gravity flowing through these 2 lines. So we need the flow control valves. Injection pump selection and operational considerations. The injection pump will almost always be a small, inexpensive booster pump and can be selected and operated without fear of overload. The pump should be selected, however, so that at least 4 foot to 5 foot restrictive head is placed against it by the injection riser, flow control, and injection line riser balance valve. So we need 4 to 5 feet of pressure drop. When this guy runs, this balance valve, this check valve, and this check valve need to put 4 to 5 feet of drop across this pump at 10 GPM. You'll have to have that in order to be able to size a pump that can do that. Okay. Time operation of the injection pump will be dictated by the differential precision of its controlling device and the rate of injected flow. The injection pump, okay, this is another good point. Injection pump should always operate for at least 30 seconds per time cycle to allow its motor to change from start to operating windings. So you can't just clatter it, every 2 or 3 or 10, 5, 10, 15 seconds. When that pump starts, it needs to stay on for 30 seconds at least, if not longer. And so you're going to have to consider that on all these flow rates and the timing. And, if I'm going to run that thing for, say, 30, maybe safely, I've said I'm going to run it 45 seconds. Well, at that flow, how much heat am I putting into that secondary? And once that's in there, then it's going to, if that's a continuously operating secondary pump, then that's going to go through the coil and you're going to get a subsequent amount of heat into your space. So that has to be factored in to your sizing calculations. The fact that you can't. Now, you could put a VFD on that thing, but these really small pumps, I mean, this could be a fractional horsepower. This could be a really small, and you're probably not going to see a VFD on that. There are some other types of motors, ECM motors and such, that do have some variable speed capability. So that could be an option in this case. Okay, injection pump applications. Let's see what else we've got here. The injection pump is finding increasing use in both industrial and commercial application. Some generalized applications are shown below. Reset control secondary zone. So again, we've got our dual bulb controller. We're simply pumping this all the time, gives us freeze protection. And I simply pop the injection pump on and off in order to set my water temperature based on outside air. So we've kind of talked about that. Okay, reheat or space temperature control air handling unit. Okay, so reheat, energy-wise, reheat is a 4-letter word, even though it has 6 letters. Because that means you're mechanically cooling air and then you're mechanically heating air. Well, you're paying money to cool it down, you're paying money to heat it back up again. Sounds expensive to me. Well, okay, and so we do that, and you know why we do that. Out of psychometrics, we do that for humidity control. Like in the library, we don't want the old books to crumble, so we have a humidistat and we have a space temperature setting. So the humidistat controls how cold we make the air to get the moisture out of it, and then the thermostat controls how warm we got to make it in order to not freeze people to death in the space. Okay, so we can use this injection pump in this sort of an arena. So the first coil over here on the left would be the cooling coil, making the air cold, and then the coil on the right with the injection pump and all that is the heating coil. And we're going to pump it continuously, and then we're just going to put shots of heat in there in order to give us the temperature of the discharge air, or that could be that thermostat could be in the space, either one. Righty. Circulated domestic water, storage tank. So, big buildings, I've got a little circulating pump in my house because it's pretty far from one end to the other. And so if you don't have a circulating pump, then all of the water sits there dead in the pipe and gets cold. And the poor guy up on the top floor, you've been in a motel where you want to take a shower in the morning, you turn the hot water on, and it's like 5 minutes later, you still don't have hot water. Well, they either don't have a circulating pump, it's not working, or they have a circulating pump and you're still far enough from where the hot water is circulating that it takes forever to get you hot water. So, in a high-rise apartment building, you may have a large domestic hot water storage tank, and here's your recycle line, and this is my makeup line where I would put, as the makeup water would come in to the tank, and I heat it up. I can pull on this side, I'm pulling some water out of the tank, putting it through the shell and tube heat exchanger, putting it back in, and this is my heat source. So, wild flow heat source. What does wild flow mean? Woohoo! It's really getting it. A wild coil or a wild flow heat source has no control. Whatever it runs, whatever you need the max, it just runs through there all the time. You were too cheap to put control on it. Okay, so you're taking that crossover flow, you're running it through that heat exchanger. You can take heat out or you can not take heat out depending on running that injection pump. And so this other is a continuous circulating pump that's just pumping water, and it keeps this tank mixed. Say when you're pumping that through there, it's going to mix all that water up, and then you've got some you're measuring the temperature of it. When it gets too cold, you turn on this pump and that puts a shot of heat into this water that's circulating, and you maintain your tank temperature. But a wild source, a wild flow heat source is one with no control. You just have maximum capability all the time. Now, you could be doing some sort of temperature reset on the primary, which would affect capacity of it. But if it's a domestic water situation, maybe not. Anyway, that's what's going on there. Lots of good stuff here. Okay, how are we doing? We'll go a couple more here. Figure 55, instantaneous domestic water controlled from the shell side. So this is where you just make hot water when you need it, okay? And so this is my circulating water pump. So I've got hot water in this system. I'm circulating it back. I've got some cold water makeup, pressure falls. We bleed the cold water in. It goes through the instantaneous heat exchanger. Looks like we're saying it's set on 140. So this is my temperature set point. Here's my continuous operation. I'm going to pump this all the time. And so if the temperature falls, then this pump runs, and I pull some hot water, put it into this continuously circulating loop, and then send the return back to the boiler to be reheated. So you can do that. Let's see. Industrial fluid temperature control, pump capacities equal max fluid draw rate. Okay. Oh my goodness. Let's see. So here is our heat exchanger. So we're just flowing max flow rate through here. So we've got heat available. This is the fluid going out into my system. I'm going to pump this continuously. Looks like I'm coming this way. And if the temperature gets too cold, I'm going to run this pump. I'm going to put heat into it, and then I pull out my system and I come back from my system. So you can do that. Okay, I think that's probably about enough for today. We'll go as far as we can next time, and then that's what we'll cover on the final. Hopefully I can get through most of it. This thing tends to go pretty quick. So hope everybody has a great rest of the day, and we'll see you next time. Take care.
How will the questions be covered over this?